calculation of friction reduction with multi-layer shells. The previous video introduced the principle of converting heat to electricity using centrifugal force and addressed some readers' questions, such as how to increase energy output and the potential output energy with current materials and technologies. It also explained how reducing the radius can lower friction losses. Today, we will introduce another method to reduce energy loss from air friction. This method explains why adding an outer shell can reduce friction, and why using multiple layers is even more effective. The most direct way to eliminate air friction is to place the generator in a vacuum. Since the process involves converting heat into electricity, continuous heat transfer to the generator is required. If heat transfer relies solely on thermal radiation through a vacuum, the transfer rate may be relatively poor. If the system can remain in contact with air, conductive heat transfer could improve heat transfer efficiency. Next, let us examine some characteristics of air resistance in rotating bodies. Consider the disc-shaped generator shown in the diagram. When rotating rapidly, the air near the surface is driven outward by centrifugal force. After the gas on the surface of the disc is removed, it will be replenished by the gas flowing downward from above, forming an airflow in the direction indicated by the blue arrows in the diagram. Because this airflow accelerates the stationary air above when it contacts the disc, the energy for this acceleration becomes the main energy loss. This energy loss, when the disc radius is 25 mm, the disc surface is smooth, and the rotational speed is 600 revolutions per minute, results in a torque value of approximately 1.63925 times 10 to the power of -4 Newton-meters, reference 1. The energy loss rate due to friction can be calculated as the product of torque and rotational speed, which is 1.02997 times 10 to the power of -2 watts. If we change the structure that causes large-scale gas flow to the structure shown on the left, where there is an inner shell rotating at the same speed as the generator, and an outer shell that does not rotate, then there will be no large-scale gas flow as previously mentioned. If the gap between the inner and outer shells is kept sufficiently small, the air between the layers would only exhibit laminar flow with no turbulence, significantly reducing the energy loss rate due to friction. Let us calculate the energy loss rate due to friction under laminar flow conditions for the same parameters, radius of 25 mm and rotational speed of 600 revolutions per minute. Assume the gap between the inner and outer shells is h equals 1 mm, and the rotational speed of the inner shell is represented by omega. Then the surface velocity at radius r is v equals r multiplied by omega. From reference data, the air viscosity coefficient is mu sub air equals 1.7 times 10 to the power of -5 Pascal seconds, reference 2. The resistance per unit area on the inner shell surface at radius r can be expressed as dF equals mu sub air multiplied by V divided by H multiplied by the, reference 3. Therefore, dF equals 2 pi r squared multiplied by mu sub air multiplied by omega divided by H multiplied by dr. The sum of the torques on the upper and lower surfaces can be derived as shown in equation 1. From equation 1, it can be observed that the torque is the integration of resistance over the radius from the center to the edge, resulting in a first-order dependency on angular velocity, multiplied by the fourth power of the disk radius, air viscosity, and divided by the gap between the inner and outer shells. The frictional energy loss rate, calculated as the torque multiplied by angular velocity, is shown in equation 2. substituting the previously chosen parameters and the air viscosity value into equation 2, the friction energy loss rate under laminar flow is approximately 8.236 times 10 to the power of negative 5 watts, about 1/125th of the measured value. This structure can be further adjusted to reduce friction energy losses even more. Consider the multi-layer shell structure shown in the diagram. The innermost shell rotates synchronously with the generator, the outermost shell remains stationary, and the intermediate layers are driven by air resistance. Their rotational angular velocities gradually increase in an arithmetic progression from the outermost to the innermost layer when stable. Define the outermost layer as the first layer, I equals 1, the second layer inward as I equals 2, and so on, with the innermost layer being I equals n, where n is the total number of layers. When the rotation stabilizes, the angular velocity of the ith layer is omega multiplied by I-1 divided by n-1. In calculating friction energy losses, only the friction on the innermost layer needs to be considered since the relative rotational speed between layers becomes omega divided by n-1. The resistance on the innermost layer becomes F divided by n-1, and the total torque on the innermost layer is given in equation 3. The energy loss rate due to friction is expressed in equation 4. For n equals 5 as an example, the friction energy loss rate is approximately 2.059 times 10 to the power of negative 5 watts, about 1/600th of the measured value. Thus, adding shells or multiple layers of shells allows the intermediate shells to rotate naturally due to friction. The more layers there are, the lower the energy loss rate.